So my work in this class is titled as a survey of techniques for fault tolerance algorithms in the embedded systems, specifically speaking in the network on chip. The reason why I have chosen this project is for the fact that network on chip has taken over system on chips in any of the embedded system designs, and the fact that the embedded systems are playing a central role in our lives these days. So I just wanted to look at the current fault tolerance algorithms implemented there and see, analyze them in depth and see what can we do to enhance those algorithms. So my agenda for today is introduction, and then we'll take a look at my approach. By my approach, we say implementing and analyzing and implementing different existing fault tolerance techniques for embedded systems and network and chip these days. And then we'll evaluate each one of them, look at the experimental results, and conclude our work. So, as I said, my objective is to have an in-depth analysis to the current fault tolerance techniques that we have implemented in network and chip. But before I start that, let me take a step back and try to define what is an embedded system. And as we all know, an embedded system is a computer system that is designed to perform, one or a few tasks, and these tasks usually function within real-time computing constraints. Embedded system these days plays a central part in our life. We can find an embedded system in pretty much everywhere. Embedded systems are implemented in cars, in airplanes, in medical devices. They're implemented in weapons control. So they pretty much control everything that we have in our life. One aspect that we should always consider very carefully when we talk about an embedded system versus talking about the general system, which is the fact that the embedded system should always function within a time constraints. It's always expected to perform correctly, returns the right results within a very limited time constraints. If you think about it, pick an example as a medical device. A medical device as a hard case that a lot of people with heart problems use these days. If that device does not return the right results and functions properly within a very limited time constraints, the consequence to that is a life of a person. Another thing that we have always to remember is that a lot of these embedded systems are expected to be functioning in a very harsh environment. The very high temperatures, a lot of shock in that environment, and also a lot of crosstalk, EMI, and etc. So any embedded system design is expected, any embedded system actually, is expected to work under these harsh environments circumstances and still expected to perform properly and return the right results. So to conclude or summarize what I have just said about the embedded systems in one line, a reliable functioning of any real-time system is of a paramount concern to the millions of our lives. Speaking of that, in any embedded system, historically speaking, you have always used a system on chip. But as technology scales and we're moving forward, system on chip is suffering from a lot of problems. The fact, and mainly speaking, system on chip does not scale with the current technology that we have these days. The fact that we have a lot of wires that we have to think about how to place them on a very small, tiny chip, how can we place those wires in the best way in order to minimize the crosstalk? Also, having a lot of wires means having a lot of energy going through those wires, which means a lot of thermal management issues that we have to think about. Also, a lot of power consumptions. So, system on chip does not really scale to the current technology that we have. The solution to that is a network on chip. So what is a network on chip? A network on chip is a new approach to design the communication subsystems on any system on a chip. And usually a network on chip-based system can accommodate a multiple asynchronous clocking that many of today's complex system designers use. There's one thing that I forgot to talk about in system on chip, which is the fact also the clock skew that any system on chip can suffer from. Having to synchronize a clock on a lot of wires and have that clock getting into the gates at the same time is not a simple issue to deal with when you design a system on chip. So a network on chip would provide us with that solution where we can have, increase our performance, decrease our power consumption, and and solve the problems with heat. And the reason for that is network on chip can help us to elegantly separate the problems in communication and computing. So in system on chip, all these problems that we talked about, how can we place the wires on that chip? How can we solve the power consumption issues generated by having a lot of wires on that chip? Network on chip will help us separate these concerns. Now, and much less to talk, when we talk, another thing to mention when we talk about a lot of these wires is that we're just talking about communication. What about computing power on that chip that we have? So network on chip will help us forget about the communication power, problems that we have on any chip and just think about computation, because a lot of these problems are eliminated by using network on chip. Intuitively, when you say a network, it means that there's routing. And when you have routing on a network, you should have routing algorithms for that. So, and of course, just like any other system that we have, when you have a chip, you have a fault. And network on chip, just like any other system, suffers from three types of faults, which are the transient, intermittent, and permanent. And also any existing routing algorithms that we have these days can be classified based on many criteria. But for my work, I've taken the route of classifying them based on their adaptiveness. So to that extent, we have three types of algorithms. They're the non-adaptive. An example to that is the XY algorithm. Partial adaptive, like the n-walk algorithm, n-random walk algorithm, and then a fully adaptive, which is the fully adaptive routing scheme with routing tables. So let's speak into each one of them and see how do they work. For the XY algorithm, I think the main thing that we should talk about when we mention an XY algorithm is the fact that it's a non-fault tolerant algorithm. And that means that if we have a problem, if there's a fault on the chip or on the path between a source and a destination, the XY algorithm does not provide any means to solve that. But why I'm putting it here, why am I classifying it as a fault tolerance, mentioning it in my work, we will see that as we proceed in this presentation. XY algorithm is a deterministic algorithm, meaning that once we figure out a path between a source and a destination, this path will be always used to route any packet between this source and destination. So it's sort of it's not a static, but a static route. A good point to mention about XY algorithm is that it's based on the Dijkstra shorted path algorithm. So we're always guaranteed that we're going to take the minimum path between the source and the destination. The way that the XY algorithm basically works is, and anytime we want to send a packet between the from the X source to a Y destination, we always take the X axis first. And it doesn't matter whether we're going in the positive direction or the negative direction, but the main point is to take the X axis all the way until the offset is 0 and make a one turn into the Y axis to get to our destination. This is basically how the XY algorithm works. XY algorithm always provides us with a deadlock-free, and that comes from the, and what we mean by a deadlock-free, it's a loop-free. So there is no loops in XY algorithm, and it comes from the fact that we are always making a one turn. And we know if you want to have if we have a loop, you will have to have like a lot of turns, right? But the fact that XY algorithm allows us to only make one turn, that means that it's deadlock-free. A good thing to mention about XY algorithm is very easy to implement, and if it's very easy to implement, it means that it's a very power conservative, because we do not require a lot of overhead to implement it. And the overhead that we need is a 250 silicon area. And what I mean by silicon area is the area of a NAND gate. So basically, the overhead is 250 by the area of a NAND gate, two-liquid NAND gate, specifically speaking. This is a very quick example about the XY algorithm. And if we take a look here, and suppose that we're going from 5.4 to 2.0. So here's the source, here's the destination, and as you can see, we're always taking the x-axis until the offset is 0, and we're making it to on the y-axis to the source. There's one point that I have to mention here in the XY algorithm, which is the fact that XY algorithm does not provide us with any load balancing. That means that every time you're sending, the same path could be used by multiple sources to route into different destinations. So that means that we can actually congest that route or congest that link without knowing that we're doing that. Which means that every time you congest a path, the packet. Let me show you another example here. So suppose that we're going from 6.3 to 1.5, and as you can see, router 2.3 is being used by 5.4 and 6.3, so we are congesting this route on a multiple outgoing channels for 2.3, whether we're going from the east or we're coming from the north. So this means that each time that a packet comes from 6.3, and then another packet comes from 5.4, the packet coming from router 5.4 will be blocked until the path will be cleared, and then it can use the path. This means increased latency for the fact that we do not care about the load balancing while using XY algorithm. The next algorithm is the negative first algorithm. It's one of the turn model algorithms, meaning that if we, as I mentioned a little bit before, if we have, our network is a 2x2 mesh, which means that the path that we can send the packets is really depicted here. We can either go north and make it to the west, or we can go north and make it to the east. We can go south, west, and then we can go south, east. So, and this is the way basically that any loop could be generated in the mesh. If you allow the packet to go in any direction it chooses, then we will end up having deadlocks. So the turn model algorithms are based on the fact that, again, you allow your packet to go only in two directions. And once they go in, they can go they can go only in those two different directions. And if they make a turn on the opposite directions, the packet will be dropped. So the negative first algorithm is slightly different from the XY algorithm in the sense that when you want to send a packet, you are always going to the negative direction. So suppose that we want to send a packet from this source to the destination. There are two different ways that we can do. We can go this way, north, and then we can go to the destination. And if you count the distance, you will find out that it's even shorter than taking this path that is illustrated in green. But the outcome or the advantages of using the negative first algorithm is that yes, you're not taking the minimum path, but you are creating more paths to the destination. So now, and the justification to that is if you have this source, all the routers that each time, the closer you get to the router, to the destination, the more congested those links are. So if you create another path, even though it's longer and it's not minimum, then you are sort of loading the balance and helping in lowering the congestion rate on any network. Any questions so far?
So when you say a network on a chip, so is it something that exists now, or is it something that is being proposed?
There are some implementations for a network.
So who are the